this problem on the board, you can answer this by writing in full sentences, by giving me bullet points, by drawing me a nice picture that's really well labeled. Whatever is your jam, we'll go over this in about 1 minute, so get her cooking. Let me show you a way that you can get 100% credit on this, should this be a test question, which it used to be. Okay, so I drew some feet, whatever. These were really my feet, they'd be way hairier. I'm just kidding. I'm not, though. Anyways, here's what's going on. Okay, your foot, relatively speaking, is the high temp. Yes? It should be a higher temp than any part of the bathroom. This tile is low temperature compared to your foot. So is this rug. So is this rug. Which direction does heat always go? High temp to low temp, always and forever. So the heat is going from your foot to the tile. The heat is going from your foot to the rug. So that's not different. Everything's exactly the same so far. The difference is, when it's going to the tile, this is very fast. That heat is transferring from your foot to the tile like that. Boom! That's why it feels cold. Here, this is slow. And so maybe I'd say a little something like this. Insulator, I'd spell that whole thing out probably. And like this, conductor. Again, I read that whole word out, I just kind of ran out of room. If you drew this and gave me these labels, fast, slow, high, low, conductor, insulator, this right here, without any other words, would be a 100% full credit explanation. This is perfect. It's exactly what's happening. Or you could go the route like Olivia was speaking like full sentences. That was great too. Loved it. Okay? Loved it. So again, feels colder, feels warmer. Are they the same temperature, the rug and the tile? Yes, they are. They are the same temperature. They are been in the same room, okay, overnight. You know, they're going to be the exact same temperature. That room temperature was probably about 25 degrees Celsius. It's going to be lower than you, which is roughly 37 degrees Celsius. They're the same temperature, so be careful. I'll have people draw this perfect picture for me, and be like, and plus the tile is a lower temperature than the, no. Same temperature, tile and rug, same temperature. So watch out for that. Very good, very good. And it's kind of nice to be able to explain that. Like, you know, you go through these experiences at home, you're like, oh, that's cold, oh, that's hot, cold, hot. And he's like, oh, I get that. Like, I can explain, like, why that is. It's kind of nice. I like it. Okay, here we are. ThermoChem, that's number 2. Exo, endo, and entropy, baby. So we're going to be hitting a lot of terms today. Not as many as yesterday, I promise. But we will be hitting quite a few. And again, just like yesterday, you're going to be able to explain more things that go down at your house than you were when you walked into class today. And that's really nice. Now, before we get started, I want to point a couple things out. Woo! Everyone look at me. Look at me. I'm lighting a candle. Okay. I'm putting that lighter there. I'm not going to touch it anymore. Hey, look. I got ice cubes. I put ice cubes on my desk. I'm not going to touch them. All right? You guys impressed? Ice cubes, candle, sweet. We'll talk about them later. Now, we got to talk about what it means to be part of the system. The system refers to the chemicals or the reaction. Okay? And the surroundings would be everything outside of the system. So everything is either part of the system or the surroundings. I would like to say that these are the most important terms of today. You must be able to understand these two. Okay? Now these are just descriptions. The system in one situation may not be the system in another. Okay? It's all relative. But these are very important. You don't have to write this down in black, but the idea is you can't mix these two up because you'll have to explain why things are happening in the way that they are. And if you don't know which one's the system and which one's the surrounding, or you mix those up, you'll cause yourself a lot of confusion. Now, here's a picture that you don't need to draw. Let's say I had a Ziploc baggie with a bunch of chemicals in it. This is actually going to be you on Thursday. Hey, you cohort B people, that'll be you next Thursday. But you folks will be this Thursday. Okay? You're going to have a bunch of chemicals in a Ziploc baggie. You're going to seal it up. The chemicals in that baggie, the air in that baggie, okay, all that stuff in that baggie, that would be the system, okay? All the stuff that's in there, that would be your system. Everything else, so like here's your paw, Okay, here's your paw, that's surroundings. The air, the class, everything else, surroundings, okay? But in this situation, this would be your system. It's basically the reaction itself, okay? This doesn't mean that every time you have a Ziploc baggie in life, that's your system, okay? I'm just saying in this example, that is your system. Sometimes your paw is the system, it just depends, okay? All right. Now we got to talk about exothermic reactions or processes. Now, what's it mean when you see an exit sign? If you're walking towards an exit sign, you're walking towards what, always? The place where you leave. But if you're walking towards an exit sign, you're always walking towards what? What are you always walking towards?
The exit.
The exit, which means you're about to go outside, right? Okay? Exit signs are called exit signs because exo means out. There you go, you learned something. Thermic is referring to heat. So this is out heat, or heat going out. Let me elaborate. To be very specific, this is when energy is exiting the system. The system. Exiting the system. It's exiting the system. Which means that it's going into the surroundings, okay? So that's why you need to know which one's the system and the surroundings, because it's exiting the system. Exiting the system. Okay? So another way to say this is that this is exothermic reactions are releasing energy in the form of heat. And just for the record, they will not always feel hot, okay? Just because something feels cold does not mean it's not exothermic, okay? I just want you to know that. So sometimes people think, oh, exothermic's always hot. We're like, well, not necessarily, okay? It depends. You guys don't have to write this in blue, but Mr. Craiglow, so we have A plus B, yield sign C plus D. What do we call A plus B again? I know it's up there somewhere.
It is.
Starts with an R.
Reactants.
There you go. And then C plus D?
Products.
You got it. I was like, it's right there. I can see it, okay? So remember this, reactants and products. Now, I would like you to draw this graph. It's very simple, okay? Just get like a little L for the graph. Have a little straight line, a nice hill, and then a second straight line that's lower than the first, okay? And as you do that, let me explain. So we got energy on our Y. The reaction is just proceeding, or sort of like time on the X, okay? The reactants are here, the products are here. So what this is saying is that the energy started here, and the energy ended here. So what happened? This gap right here between the reactants and the products, that is energy exiting your system, okay? In other words, you started with more energy and you lost some during the process of the reaction, and your products don't have as much energy as the reactants. It's exothermic. Energy exited your system. So in exothermic reactions, reactants have more energy than the products. The reactants will always have more energy than the products. So I could ask you to draw this graph, be like, hey, draw me an exothermic graph. Or it could be like, which one of these is an exothermic graph? Or you look at a problem, you realize it's exothermic, and then you're asked to pick the graph that matches the reaction you just studied. A lot of ways we could talk about this. Some examples: fire, calcium chloride, hand warmers. You don't really have to write that down, but the candle, for example, on my desk that's lit is exothermic, okay? Because heat is exiting that candle. And if I put my hand right here, I feel heat hitting my hand because it's leaving the candle and it's going out to its surroundings. So in this example, the candle is the system, and everything else, my desk, the air in the room, my paw, are surroundings. Now the next slide will be easy for you. Oh, actually, no, here. Let me give you a little picture. This is a hand warmer. Okay, you guys ever use hand warmers? Okay, here's what a hand warmer is. It gets a high temp, your surroundings, so maybe that's your paws, a lower temp, and the energy will exit that hand warmer. This system is exiting, so this is an exothermic reaction. That makes sense, right? All right, now this next slide, you can see where we're going. Endothermic. Endo, I think you all realize at this moment, talking about in, again, thermic's talking about heat. This is heat going in. Or what I like to say is energy entering, En. Endothermic, entering the system from the surroundings. So that means your system is taking energy in. Again, it's always from the perspective of the system. It's always from the perspective of the system. So some people would say the system is absorbing energy from the surroundings. So last time we said releases energy for exothermic. Now we're saying absorbs energy. And again, just like exothermic reactions don't always feel hot, endothermic reactions will not always feel cold either. Okay? It depends. Your paw is a higher or a lower temperature than whatever your system is. And here, take a look at this graph. It will look similar, but the key difference is it will start low and end up, have the little hill and end up higher. So it's still energy on the Y, still the reaction on the X. But here, what we're seeing is this gap is now not energy exiting, but that's energy entering. Energy enters. And so, before, the reactants had more energy than the products. Now, the products have more energy than the reactants. Exothermic, endothermic, yin, yang, they are opposites. They are opposites. Example of this, baking soda and water, an ice pack maybe, something like that. Something like that. And you can say the temperature around the system will decrease, which makes sense because the system has energy entering it. So that means the surroundings temperature will go down as the temperature of the system will go up. All right. All right. We all good with this? Quite a lot. But we will do lots of practice to sort of solidify a lot of these ideas. Again, a cold pack is made of ammonium nitrate. A cold pack is it's a relatively high or low temperature cold pack. It's what? So it's got the L. That means the surroundings are H. Which direction is heat always going? High or low. And so you can literally just watch the arrows going into the system. So that will help you remember it's endothermic. When in doubt, find your L, find your H, and that will always help you find your way in terms of whether something's endothermic or exothermic. Don't think to yourself, oh, that would be cold or that would be hot. Think about low temp and high temp in the situation, and you can't go wrong. It's always high to low. Now we got to start talking about some weird stuff. Entropy. Entropy, which means disorder. Now I got a question here. Does anyone have a really messy room? Okay, I knew it. I knew it! I was looking right at her. I was like, okay. And let me guess, does anyone have a really clean room? You, really? Not you? Surprising. Man, you guys have a clean room? Okay, all right, pretty clean room. Wait, Stickney, you got a clean room or a messy room?
Clean.
Clean, okay. I can see that. I can see that. Okay. Well, disorder is a measure of randomness or disorder. I'm sorry, entropy is a measure of randomness or disorder. The more disordered, the greater the entropy. The more disordered, the greater the entropy. And so what I'm trying to say is, if you got a messy room, it's very disordered, and that means you have a large amount of entropy. That's what that means. Entropy is disorder, or chaos, craziness. So entropy is disorder. High entropy means high disorder. Do not have to draw this right here. Here's an example. Let's say I have a brick wall where it's a nice 90-degree angle. Every brick is put neatly together. This would be a low entropy situation. A pile of bricks, there's no order, it's just randomness. That is a high entropy situation. We got Stickney's room over here. And we got some Uzama over here. Okay? I'm really surprised. I would have thought you had like a pristine, Surprised by that, Crazy. You learn something new every day. Okay. So now we got to talk a little bit about phases. Phases. Don't write all this mess up here. These are just links I don't want to forget, so I always put them there. Okay. So we got to talk about different phases or states of matter. So crystals have the lowest disorder. We're going to do a little ranking system, okay? So leave yourself some space to the right. You're going to have 5 spaces total, crystals being the first. So crystals have really low disorder, really low entropy. And I would like you to sort of put the little number 1 next to crystals and be like, okay, if I had to put a number on it, again, I'm making this number up. This is a Mr. Pilcher number. I just give them the lowest number I can, be like, oh, they're like a 1. They're like a 1 on the entropy scale, really low, really low. Next up, we got solids, okay? They're very low still. They're like a 2. Why are crystals lower than solids? Well, crystals have like these beautiful, regular, repeating patterns in them, whereas solids are just sort of like piles. They're all nice and connected. Like your desk, okay, it has a lot of order to it. It's not like Olivia goes to sharpen her pencil and she comes back and her desk has changed shapes on her. Like, oh, I just felt like this shape was better. Like, no, that's not how solids work. Like, they are there, they're ordered, they're not moving around. Like, they have a lot of order to them. They're not quite as beautiful as a crystal, but they're pretty close. They're pretty close. And if you think about it, if I pull up my PET simulation here, here's a solid, right? Not really going anywhere, lots of structure. Again, can you kind of see how they're vibrating a little bit, like I talked about yesterday? But pretty ordered. A liquid, on the other hand, has a lot more entropy. We're moving around a little bit. That's why liquids can take the shapes of containers they're in. So they can move around a little bit. They have a little more leeway. Like this little guy's going rogue over here. They're mostly still on a little pile here, but sometimes they kind of, get a little saucy, do a little jumping jacks here and there. And so that is why liquids are next. And they're like a 5 on the entropy scale. So they're, higher than crystals and solids for sure. But, nothing to write home about in terms of entropy. And a lot of people are thinking to themselves, oh, he's going to write gases next. And that is not the case. We have aqueous solutions next. Aqueous solutions, which are like a 10 on the entropy scale. So we're kind of getting up there. You see how we're kind of skyrocketing here. Aqueous solutions are a lot more disordered than a solid or a crystal. Let me show you why that is. I'll come back to this if you didn't get all of this written down just yet. So again, if I'm looking at a solution here, okay, so this is salt in here. I got some NaCl. This is pure water. Okay, so pure water, 5 on the entropy scale. Okay, it's a pure liquid. No matter what, if I grab some out of here, I'm going to get an H2O, no matter what. Okay, but if I do one of these, I shake some salt in there, get some big crystals. Watch what happens. Those crystals hit the water, and they break apart into tiny little pieces, and they start moving all around that solution. Okay, so you see how this has a lot more disorder to it than just pure H2O. So that's why solution, an aqueous solution, is higher on the entropy scale. It's got more disorder. It's like a 10. And then, of course, you do have gases, which are incredibly disordered. They're freaking out, hitting the sides of that container. Pew, 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 pew. It's like a little ping pong ball. 35 on the scale. Just way higher than everything else. Way higher than everything else. Okay? If this was your room, okay, this means you haven't seen the floor in years. Okay, that's you. If you're a gas on the entropy scale, that's you. You haven't seen your floor. You might even know where your house is. I don't know. Like, oh yeah, my room's just kind of like, sometimes it's the bathroom, sometimes, just wherever I fall asleep, Like, okay, well, you have a lot of entropy in your life. Anyways, so that's our entropy there. Now, general rule. Nature loves reactions that create more entropy. They love to spread entropy. Okay? Nature loves to spread entropy. So if we can get a solid to become a liquid, nature's down with that. If we can get a liquid to become a gas, nature is super down with that. Nature loves to spread entropy. Loves it. Loves it. Winner, winner, chicken dinner. Okay. Now we got to talk about spontaneous. This is an E after the N. It looks like a C. It's not. It just got a little goofed up. That E's been through some rough times. Spontaneous.
Mr. P,
Yes.
can you go back for a second? I missed the last thing that you said about nature.
Absolutely. Nature loves to spread entropy. So nature favors reactions that are increased entropy. And you don't have to write down that whole sentence there, Lacquer, just whatever. I think that was Lacquer, right? Was that Lacquer? I think it was.
Yeah, thank you.
No problem. Starting to recognize people's voices. We're getting there. Spontaneous. If something's spontaneous, that means it's a process that occurs without any ongoing outside intervention. I would like you guys to remember the beginning of class. You remember when I lit that candle? I showed it off. Check it out, virtual people. Woo, woo, woo. Lit candle. Anyways. Okay. Well, I got wax on my finger. That's fine. So, yes, I lit that candle. Okay. But have I had to relight that candle? Did I relight that candle? I haven't touched that lighter since I lit it in the first place. So, a candle burning is spontaneous because maybe I have to kind of get it started. But as long as I don't have to have ongoing outside intervention, I don't have to intervene every so often, it's a spontaneous reaction. It will just happen naturally. Hey, I took ice cubes, slapped them on the desk. You'll never guess what happened. Aurora's like, why did you do that? Okay, they melted. Did I have to like, okay, time to melt. You got it, little buddy. Like, did I have to encourage the ice cubes to do that? No, I did not. That was a spontaneous process because it occurred naturally. I did have to grab them out of the freezer and plop them right there, but after I did that, it just happened on its own. So ice cubes melting, candles burning, those are a couple of examples of spontaneous processes. Now there are two factors that contribute to spontaneity. There are two things that will cause something to be spontaneous. Now before I mention those two things, I just want to share with you something about the universe. The universe loves to spread entropy, as I just mentioned before in the last slide, and it loves to spread heat. Do you remember those two things? That'll help you out quite a bit. The universe loves to spread heat, and it loves to spread entropy. It loves to spread heat and entropy, chaos, disorder, whatever. Okay? So it loves to spread those two things out. Okay, there are two factors that will influence whether something happens naturally, spontaneously, or not. Exothermic processes and an increase in entropy. Nature loves these two things. Again, when I said spread heat, that's the same thing as saying an exothermic process, right? Because the heat is exiting the system and going out into the universe, the surroundings. And it loves an increase in entropy. The universe loves those two things. Loves it. Loves it! All right. Sometimes these two things will work together. Sometimes. Sometimes they will not. It depends. And I love talking about this, spontaneity, because it explains so many things. And you guys are actually going to enjoy it too, I think. So let's talk about an example. Now, ice cube melting on my counter. Did the ice cube melt without me helping it melt? So that means it's what? It is a what kind of reaction? Spontaneous. Okay? So yes, the ice cube melting is spontaneous, as I already mentioned, because it happened without me having to continually help it happen. I started it, I put the ice cube on the desk, that's it though. Okay, so here's how you need to think about this. The moment you learn something is spontaneous, you'd be like, okay, that means it is either exothermic, or it's an increase in entropy, or both. Okay? But at least one of these things has to be true. If this happens spontaneously, it's either that, or it could be both. But it's got to be at least one. Make sense? Let's think about why this reaction happens spontaneously. So your kid brother is like, hey, why do ice cubes melt? Now you'll actually be able to explain that. Before, when we walked into class, you're like, I don't know, they just like that they do. Here's why. Okay, number one, let's think about it. Is an ice cube melting endothermic or exothermic? Endo or exo? Let's see here. Aurora? Endothermic. Why do you say that? Think about it. Where is the low temperature, relatively speaking? Is it the ice cube or the counter? There's the L, right? That means the counter has to be the H. Where does energy always go? High or low? You can literally see it's entering the ice cube. Makes sense? So ice cube is endothermic. An ice cube melting that is endothermic. So it's not exothermic. Nature's not a big fan of that. So that means it has to be what? It has to be an increase in entropy. And let's just make sure that that does make sense. Think about it. Okay? An ice cube is a solid. It's going to a liquid. That's an increase in entropy, isn't it? You're going from a 2 to a 5. Oh, okay. Well, yeah, I guess that makes sense. So the reason why an ice cube melting is spontaneous is not because it's endothermic, but because it's an increase in entropy. That is why it's endothermic. Or that is why it's spontaneous. That's why it just happens. Kind of makes sense, right? The universe loves to spread heat and entropy. If it's not spreading heat, in this case it's not, it must be spreading entropy. All right. What about this one? Why is the process that a heat pack goes through sodium acetate spontaneous? Here's the equation for a heat pack. You have sodium acetate aqueous solution. And all it does is it becomes like a crystal sodium acetate. It basically it becomes a solid. So it just goes from aqueous to solid, and it will give off heat when it does that. Okay. So talk to me about the entropy. Is this an increase or a decrease in entropy? What is it? It's a decrease, right? Think about it. This is like a 10 on our scale. Again, I made that number up, but it kind of helps with these. This is like a 2. Definitely a decrease, right? So this is a decrease in entropy, so that's not why, because it's creating less disorder. So you think to yourself, oh, it must be exothermic. Okay? And let me double check and make sure that's the case. Well, again, we're going from here back to there. That's quite a decrease. It was exothermic. And does that make sense? Does that make sense? Well, here's my heat pack. By the way, when I draw systems, I like to just draw a square. Keep it simple. Even if it's like a ball or something, I just draw a square. Okay? Well, here's my heat pack. It is relatively, temperature-wise, hot. My paw, oh, hello. There we go. My paw is a low temperature. The heat will then leave that heat pack and go this way. It's exothermic. Makes perfect sense. So if I was like, Billy, why is this process spontaneous? You'd be like, well, it's a decrease in entropy, but it's exothermic, so this reaction is spontaneous because it's exothermic. Make sense?